What did you say?
I have a small question about what we mean by we use the wave function to calculate the beam, right? So the wave function with the expectation values.
Yep. Yep.
So this one, like for this wave function, we mean like normalized wave function. Right?
Yes. That has to this has to mean the probability density. Yes.
So it's more like a 1 over a square, something like that.
Yes.
Because we have to normalize this. So
yes.
We calculate the expectation value, we use this.
Yes.
Okay.
You know, and it's a little bit confusing because we will refer to solutions to the time-dependent Schrodinger equation as psi of x and t.
Yeah.
But just because they're a solution doesn't mean they're normalized. And usually when we write down a formula in terms of them, we assume they're normalized.
Okay.
So that's just tradition. So if all else fails, just normalize as soon as you get a solution and then you'll be safe. Mm-hmm. So I think I'm going to have you guys hang on to problems 1 through 4, which I said are due today, until we hand in 5 through 8, just to not have so many little things for me to hang on to and grade and possibly lose. So just keep working on those. I'm happy to entertain any questions I answered. Talked with several people about it during office hours. So if anybody has questions about what I mean on those problems, feel free to ask. Not bad at all. I was down yesterday because I had a physics 110 lab in the afternoon. And, you know, there was a little bit of snow on the road at some points, and only one lane on the highway had sort of been driven over and worn down to the pavement, but it wasn't too bad. And today it was even better. It's pretty crusty, yeah. I mean, you're driving into the parking lot here on Center like that. And I have a steep driveway, so I couldn't get up my driveway last night, but as long as it doesn't snow and ice more, that's not really a problem to park on the street. I looked earlier and it was 50% chance. So I'm hoping either it doesn't happen, or if it does happen, it won't be that much. But it looks like we're gonna have to wait till Sunday for anything to really melt. We got a puppy, like many people in the pandemic, you know, in January, end of January. So it's not that old. And I was taking him for a walk last night. And I just realized, you know, at least in Lexington, it seemed like you guys got more ice here than we did in Lexington, but there was a thick layer of snow, and then it had rained right after all the snow. And so there was this thin crust of ice. And he likes to run, he sees an empty field and he runs up it. But of course, I'm up there. Every step I take, I fall down like 6 inches, and then I step another time, fall down 6 inches. It's a Shiba Inu. So it's little. I mean, it won't get more than like 20 pounds. Kind of looks like a little red fox, but except it's got a curly tail instead of a fox tail, but it's got kind of orange fur like a fox does. So it's pretty cute.
So Japanese breed?
Sorry, Elvis, I couldn't hear you. Let me turn up
Let's see.
volume. Okay, say that again.
So Japanese breed?
Japanese breed, yes. So there are several dogs that breeds that hail from Japan, and this is the smallest of them. All right. Any questions concerned about stuff? I guess a couple of people came in since I said it, but I'm going to actually collect 1 through 4 at the same time as 5 through 8, just so I don't have so many mini assignments to hold on to and grade at once. So just keep working on 5 through 8 now, and I'm happy to entertain any questions you have on 1 through 4, or even 5 through 8, if you've looked at them. So let's turn all of that in on Friday, I believe is when I had it due. And so we can answer questions about it tomorrow during our longer class too. We're still not ready. We won't be until we're in the middle of chapter 2. We won't be really ready to do MATLAB kind of stuff. So we're just going to keep going, spending our time elaborating on what's in Griffiths. So any questions before we get going? All right. So just continuing on with where we were talking about the fact that we know how to calculate rho of x, as a function of x and get that shape if somebody gives us psi, or if we know what psi of x and t is. We take the magnitude squared, and that gives us rho as a function of x. We don't know how to calculate rho as a function of px or E, or the total energy E, or as a function of kinetic energy or anything like that yet. We'll find out later on. But right now, since we don't know those, it might be interesting to see if we can figure out, and we will be able to figure out, what corresponds to the notion of the average value of the probability density function, not just as a function of x, but as a function of any dynamical variable, and also the standard deviation in terms of any dynamical variable. Forgot to turn this on, so let's see. Hold on just a second, let me go to slideshow mode. Okay, so I'm imagining a probability density function. This thing is so quirky. Probability density function as a function of some dynamical variable. And that dynamical variable isn't necessarily x or px. A generic dynamical variable that might be something like the total energy Griffiths denotes by just the generic label Q. So Q could be any function of the state of this point particle.
Dr. Kelly, I can't see the slideshow.
Oh, I'm sorry. That's because I didn't share my screen. Thanks, Alvis. And don't be shy about shouting out when that happens, because sometimes I just forget. Thank you.
Here it is.
So, if we have a probability density function, there we go, like I've shown down here, you might want to figure out what the average value of it is, which is somewhere near the center of that PDF as a function of that dynamical variable. So the average in quantum mechanics, as you know from modern physics, I assume you use the term expectation value, but expectation value means the average. And so we denote the expectation value. I'm assuming this is the same notation you used in modern. It's pretty standard. The average value of rho of x, that's sort of where you could say on average the middle of the distribution it is. It's not really the middle, that would be the median, but this is the average according to the usual definition. we denote it by those angle brackets around X. That's the average value of this distribution. If we had rho as a function of energy, the expectation value of energy would be denoted this way. Okay, so that's one way to very crudely characterize this, not giving all the details, but just saying, well, where's the main peak kind of located? You know, where's sort of the middle of the distribution in the sense of an average? Same thing with the spread. So I've just, you know, notionally noted that right here. Oh, it's somewhere near the middle of the distribution. Let's not worry about the details right now. Same thing with the spread. The spread tells us something about how wide on average the distribution is. Is it narrowly peaked? You know, the Dirac delta function, that really sharp peak, which was 0 everywhere, and then a huge spike, that would have 0 spread, 0 standard deviation, okay? But the standard deviation, a lot of times in quantum mechanics context, is referred to as the uncertainty. It means the same thing. Griffiths is a little bit unusual as he uses the Greek letter sigma with the subscript corresponding to the variable that you're considering that rho as a function of, to denote this, and he calls it the standard deviation. More traditionally, and I don't know if you did this in modern physics, you use delta x and delta e to represent, but I mean exactly the same thing. It's just Griffith's quirk that he wants to stick closer to what you'd see in a statistics class, maybe, where you talk about standard deviations. Okay, so and notionally, remember, I think I changed this on your printouts of the notes that I gave you. I had actually this listed as sigma q, but you know, if you have a Gaussian distribution, normal distribution that looks like this, sigma sort of roughly, you know, tells you this distance. And so 2 sigma, you know, sort of gives you a rough, what is it, like 68% of the probability is between plus, you know, the mean plus or minus sigma. So this distance all the way across should really kind of be, that's telling you roughly the spread size of the distribution, 2 times sigma q. Okay, so let's step through this in the way I did in the notes, and we'll just do some calculations here on the board to elaborate. You know, maybe it's not obvious to you why we're calling the expectation value, or how to calculate the expectation value of a continuous distribution. So let's go back to what everyone can agree on, which is if somebody gives you a bunch of numbers, we all know how to take the average or calculate the average. You add them up and you divide by how many numbers there were, right? That's what everybody learns the average is way back when. So what we're going to do is, I'm going to stop sharing here just for a second and show the board. Let's suppose, you know, Griffiths does this example of calculating the average age of people in a room. So let's imagine we're going to do that here. And I would say, just to make a made up example, let's imagine there are 4 people in here. We have one whose age is 18, 2 whose age are 20. Maybe we'll make 3 of them 20. And 1 who's 21 or something like that, right? And to find the average age, what I would do is add them all up and divide by 5, right? That would be the average. Now, another way to write this is, well, let's write this as 18 plus 3 times 20 plus 21 all over 5. And then I could write that as 1/5 times 18 plus 3/5 times 20 plus 1/5 times 21. And notice, at least for this distribution of ages in here, the probability of finding someone who's 18 is 1/5. So this is the probability associated with 18. We might denote this as P18. This 3/5 is the probability among this group of people of finding someone age 20. And this is the probability of finding someone age 22, 21. So we can write it as the sum over all n values, where n is 1, 2, 3, 4, 5, 6, including 18 and 20 and all that, right? Sum over all n, the probability of that particular age times the age itself. It looks a little bit weird, but that's really nothing different than a formula that tells us how to add things up and divide by the number of things that we were adding together. Looks a little bit unfamiliar. Okay, so let's go back to sharing the screen now. And if I arrow forward, that's what I have here. I wrote it in terms of the age. The expectation value for the age is the probability of each age times the age itself summed over all ages. And maybe those probabilities will be a lot of zeros, right? Here, if we start at n equals 1, P of 1 is 0, P of 2 is 0. So you might have a lot of zeros in there, that's okay. But we're still going to sum over all of them. We just showed that that's the same as adding them up and divide by n. So that's something we can all agree on. Now we want to consider a continuous distribution. For example, rho of x, and be able to apply this formula. So if I draw some notional probability density function, I'm just going to draw it as if it's a Gaussian. Here's my rho of x as a function of x. What I'm going to do to relate it to the discrete case is break this up into a bunch of little rectangles, as if I'm doing an integral, right? I'm going to sort of think of the area under the curve here as if we're going to break it up into all these little rectangles that approximate the curve. I'm not doing the best job drawing them, but they should be approximating the curve like that. Okay. And what I want to do is add up the probability of each x value. So let's make sure I'm following the notation I have in here. Let's imagine I've got, you know, a lot of different x's. So here's x sub I, here's x I plus 1, and so on. And I'm going to sum over all those x's, an infinite number of different x's, right? So the expectation value of x, that means the average value of this, we know should be equal to the sum over all these rectangles, right? And I could say I have x, you know, maybe this is, I have an x0 here, and then an x minus 1, and an x minus 2, and an x1, and an x2. So I'm going to sum from I equals minus infinity to infinity. That's going to give me sums over all those rectangles. The probability associated with the rectangle at xi times xi. That's the formula we just got. Except instead of having a, you know, at least just ages starting at 1, we have we have x values that go back to minus infinity and all the way up to plus infinity. But we said to calculate the average value, if you imagine it's discrete. So I say, just for a moment that we can only measure this x or this x or this x and so on. This is the formula we just justified a minute ago. That's the same as added up, divide by n. Now, the probability associated with this, probability of a measurement giving a value centered at xi rather than one at xi plus 1 or so on, is nothing but the area under the curve from one end to the other, right? If I want to say, what's the probability of a measurement of x being found in this region? What I would do is integrate from there to there. And that's pretty well approximated by just finding the area of the rectangle, right? The area of the rectangle is the area under the curve, which is the integral from there to there. So this is the area of the rectangle. The area of the rectangle is nothing but rho at position xi times whatever the width of this rectangle is. Let's just call that delta xi. Okay, so we've got a sum over all I of rho of xi times xi delta x, where delta x is supposed to represent the width of each one of these rectangles. Now that's an approximation, but we're going to now let delta x go to 0, and the approximation is going to become exact. So now we're going to let delta x go to 0, and the number of rectangles we're considering get larger and larger. It was infinite, but we're going to more finely subdivide it. And you know from your work in calculus that there's a symbol for the limit as delta x goes to 0, and the rectangles get smaller and smaller, and we write that as an integral. So this approaches as we let delta x get smaller and smaller, and the rectangles get smaller and smaller, as by definition, the shorthand is going to be the integral from minus infinity to infinity of rho of x times x dx. That's an agreement you made in calculus of shorthand from the limit of all those things, right? So therefore, for us, we know how to calculate rho of x, so I might even rewrite this as the integral from minus infinity to infinity. Rho of x is going to be psi times psi star times x dx, right? And we're going to write it, we'll see why in just a second, psi star times x times psi dx. You already know why I'm writing it that way, but this is the formula for the expectation value of x. And I might say if I wanted it time t0, what I would do is evaluate each of these psi's at time t0. I know I'm writing this too small, but this is supposed to be x and t0 there. Psi star at x and t0 and psi at x and t0. You evaluate it at the time you want, and that would give you the expectation value at that time. The expectation value may change because all the probability may slosh over to this side at a later time. So the expectation value as time goes on might move around on the x-axis as the wave function sloshes from one side to the other, obeying the time-dependent Schrodinger equation. Okay, so the point of that was that it's really, this really is the definition of average. That's what we mean by average. It's the same as adding them up and dividing by n, in the sense that, well, we can apply that to this infinite collection or continuous collection as long as we divide it up into discrete pieces, and then we're going to let those pieces get smaller and smaller. Okay, so that's the second step. Now, what about for the calculating the expectation value as a function of px? Well, the problem is we don't know what rho of px is yet. We know rho of x is psi star times psi, but we don't know how to calculate rho of px. We'll find that out in chapter 3, but for right now, it's something that's missing from our theory, and we're going to have to figure out what to do. What we're going to do is there's no way to write down that probability density function because we don't really know how momentum is related to the wave function at all. So we need a new postulate added to our theory. And Griffith suggests, different people postulate different things, but Griffith suggests that, well, look, I know we're describing things as waves, but we all know macroscopic particles are pretty much localized, right? When you have something that's big and you're not looking at tiny little uncertainties down at the atomic scale, the location of this is pretty well defined as time goes on, as it moves across the room. And therefore, if I'm going to think of the, if I have a state that's going to represent kind of a massive particle moving around in the room where it has a well-defined position and a well-defined momentum at all times, we certainly want it to be true that, in that case, I would imagine the wave function as being narrowly peaked around the location where we're likely to find it, right? When this piece of chalk is moving around the room, the wave function presumably is essentially 0 everywhere except right near where the chalk is. That's for a macroscopic thing. It's not going to be spread out all over the room, like for an inherently quantum mechanical kind of object. So if quantum mechanics is going to reduce down to definite motion of things, then the expectation value of the wave function should be give the exact location where that thing is in the case where the wave function is very narrowly peaked at a certain location in space. And what that means is we would expect that the expectation value of the momentum at any one time should be related to the expectation value of x in the same way it is in classical physics. So Griffiths suggests that we should postulate, there's nothing in our theory that tells us this yet, but momentum is going to, the expectation value of momentum is going to be related to the expectation value of x the same way it is in classical physics. Because if something's localized, the expectation value of that thing is like the location of that classical thing. Right? If all the probabilities in one location, that's sort of, it's behaving like a classical particle, the expectation value is going to be that location in space. So this is just saying P equals mv, essentially. We're going to postulate that and find a new expression for how to find this, because we already know something about this. Let me give you the short version, because Griffiths gives a lot more details in the book, and I don't want to spend the time working through the mathematics, but I'll tell you in summary what he does. Okay, so let's work on this right here. And sorry, Alvis, I really should stop sharing the screen so that you can see what we're doing here. The rate of change of the expectation value of x. We just found out how to calculate the expectation value of x. That's the rate of change of this integral from minus infinity to infinity of psi star of x and t times x times psi of x and t dx. Notice that this thing is not a function of time, it's not a function of x because we've integrated over x, right? This is a function of x and t. This is a function of x and t, but once I integrate over x, this integral itself is just a function of time. And that's why we can use the ordinary derivative here, okay? Now, since the integral is over x, I can actually move this time derivative through the x integral, but I have to be a little bit careful, and I don't remember if Griffiths explains this. When you move the time derivative inside the integral, you have to replace it with a partial derivative, because now what it's taking a derivative, the integrand is a function of both x and t. So you'll see in Griffiths' work, this is equal to, well, let's see. The time derivative, when I move it inside, I've got a product of three things here. This doesn't depend on time at all. In other words, there's no t's in this part. So it can pass right through the time derivative because it's the other variable in there. So we're just going to pull that out. But let's write this as just briefly as psi star psi dx. So I brought that time derivative in. It was an ordinary derivative, but when you move it through the integral, you got to make a partial derivative because now the integrand is a function of more than one variable. Here's where I'm going to leave out a lot of details, and they are in Griffiths, or at least he tells you what to do and shows most of the steps. You just have to follow different equations around. So what we're doing in this step is using the product rule. You can see that right here. We're ready to apply the product rule because we got a derivative of a product. We're going to apply the time-dependent Schrodinger equation to exchange out time derivatives of psi that come out of the product rule to spatial derivatives of psi. And then we're also going to use integration by parts. Okay, and to see where that comes in, you just have to follow the details through Griffiths. But you know, there's several steps in here that I'm leaving out. After applying those, and you know, if you want to talk about those outside of class, I'm happy to work through them with you. He gets this expression, psi star times minus I h bar over m times d dx. That derivative, or this whole thing, is just being applied to this psi that's over on the right-hand side. So this derivative, and there's some constants, those are acting on the psi to the right. They're not acting on anything to the left, because that's the way we usually denote derivatives. Okay, and so what that means is, going back to here to summarize, we've just shown that the x, you know, again, so this is what we've we've said, I guess I'm not quite there yet. This is an expression for d expectation value of x dt. What I wanted was m times that, right? When I multiply that m in, it cancels this m in the denominator, which is kind of nice. And by definition, we're going to say, we're going to postulate that that is the expectation value of px. For example, at time t0, that would mean we would evaluate these psi's at time t0. They would just be functions of x there. You evaluate them at the time that you want to find the expectation value of px. Okay, and that's what's shown on the slide there. So we now know, amazingly, we never figured out, or we haven't said yet, how to figure out what rho of px is. We haven't figured out how to say what rho of px is. We know rho of x is psi times psi, but we haven't figured out how to write down what rho of px is, and yet somehow we were able to find the center, or the expectation value, or the average of the px distribution without even knowing it. And somewhat suggestively, we're finding out here, well, look, we just threw the x in the middle here. We didn't really have to, but here this one ended up in the middle. So it seems like we're getting a trend here, as you know from modern physics. In order to find the expectation value of a variable, a variable, you've got some kind of operator that you sandwich in between psi star and psi, or at least that seems to be working for the position operator and the momentum operator. Okay, so that motivates defining some operators, right? Up to this point, we haven't talked about what operators are yet. So we're going to define the position operator to be the thing that was sandwiched in between a psi star and a psi there. It's not very exciting. It is the multiply by x operator. When it operates on a function of x and t, what you do is just take the formula for that function and multiply by x. It's not the most exciting operator. There's not much to think about. Okay, so unsharing again because I'm at the board here. We're going to define the x operator, and I'm assuming you use in modern physics, you put little hats over operator notation. Okay, just trying to connect with what you're doing in there. People write something that looks ridiculous. The x operator is x. You got to know what that means. That means when it's sitting in front of a wave function, it means multiply the formula for that wave function by the variable x, because the wave function is a function of x and t, right? The momentum operator is going to be, or maybe I could put an x down there if I really wanted to be definite, because when we're in 3 dimensions, we'll talk about y and z momentum too. It was the stuff that was sandwiched in between the psi star and the psi, by definition. That's what we're going to call the momentum operator. And it was minus I h bar derivative with respect to x. So that's our definition of the momentum operator. And again, if you put a function of x and t over here, it's just saying take the partial derivative of that formula with respect to x of whatever is following to the right. Okay. So in terms of those, why are we not going forward here? There we go. It's saying in terms of the position operator and the momentum operator down here, if you've got one of those operators to find the expectation value of that variable, you just sandwich the corresponding operator in between a psi star and psi and integrate. Okay, good. And that's amazing because we haven't found out what rho of px is yet. We will later on. I think it, in a lot of textbooks, I mean, you could say the same thing about x, right? I could have done a lowercase x hat. It's just to make it stand out more. So we tend to use capital letters for the operators. There's no good reason other than to make it stand out. It looks like something big and important. I mean, I even made it bold here. I'm not sure why I did that, but I don't think Griffiths makes it bold. Okay. Now, remember, there's not just rho of x and rho of px, but we can consider other dynamical variables too, like the total energy, like the kinetic energy, like the potential energy. All of those things are going to be functions of x and t. For those of you who are in advanced mechanics, probably all of you, the state of a point particle as it moves around is totally given at a moment by its position and momentum at that moment. If you know it's those two variables, you know everything about its state of motion at that moment, and you can predict where it's going to be at all later times, assuming you know the potential energy function. So for any other dynamical variable Q that might be like total energy or something like that, we're going to want to define an operator associated with it. So if I say the total energy is equal to, oops, I keep forgetting I got to switch back and forth here. Total energy in classical terms would be related to momentum and position by something like p squared over 2m. That's the kinetic energy. That's the same as 1/2 mv squared, right? Plus the potential energy, and it depends on what potential you're sitting in, but in this course, we're going to denote that by v of x. So this is another dynamical variable. It's a function of p and x, right? I didn't tell you explicitly what v is, but maybe it's in a harmonic oscillator potential or something like that. Same thing for kinetic energy, right? We would say the kinetic energy is a different dynamical variable. It's just p squared over 2m. It doesn't depend on x. So those are some other, important dynamical variables. The idea is any generic dynamical variable that Griffiths denotes by Q is really a function of x and p, or x and px, if you really wanted to be definite there. We're only talking about x right now, right? And if we want, just like we postulated that a classical equation relating position and momentum, that was px equals m times dx dt, was true of the expectation values in that case, we're going to want the same thing to be true for expectation values of other dynamical variables. If in classical physics a dynamical variable obeys a certain equation, then the same equation ought to be true of the expectation values in quantum mechanics if we want quantum mechanics to reduce to classical mechanics in the case where the wave functions are really sharply peaked and localized. Either the position is localized or the momentum is localized. It seems to make sense. Okay, you can't prove that, but it seems like a sensible thing to do. So if we want that to be true, relationships like this to be true, if I want this to be true of the expectation value of E as equal to the expectation value of P squared over 2m plus V of the expectation value of X, if I want things like that to be true, then that tells me the corresponding operator corresponding to this dynamical variable Q, again, we'll denote it by a capital variable, is given by the following formula. What we should do is take the formula for Q. Well, I guess we would write it this way. Take the formula for Q, and everywhere there's an X in it, I'm going to substitute the position operator. Well, that's not very exciting because that is just X, but make it explicit. And everywhere there's a PX, just like in this formula over here, I'm going to substitute the momentum operator. So just as a specific example for the total energy, let's imagine that classically, we imagine the total energy. I've got a particle. It's in a harmonic oscillator potential, right? So it's like attached to a spring, right? And there are forces that push it back to the center, and it would keep oscillating back and forth if I pulled it to one side and let it go. The relationship between the total energy variable and the momentum and the position, maybe it's, harmonic oscillator potentials are proportional to x squared. So I might just say it's some constant alpha times x squared. That's a harmonic oscillator potential. That's something that we might encounter in classical physics, right? In, what is that? Physics 340 that you guys just took in the fall, right? If that relationship is true, what I'm telling you there is this formula for Q as a function of X and PX. There's the X and there's the PX, if you really want to put the X down there, right? And that tells me that to get the operator associated with this, and you know in quantum mechanics, we don't tend to use E hat, instead we use H hat for the Hamiltonian as the associated operator. So we won't write this associated operator as E hat, but rather as H hat, corresponding to the Hamiltonian. But it means the same thing, could have been an E hat. To get that, we do the momentum operator squared over 2m plus alpha times the position operator squared. And then now that I know the formulae for those two, I can plug them in. And you got to kind of know how to square things out. When you have a derivative operator that you're squaring, it just means it applies and applies again there. So that would be minus 8 IH bar times ddx multiplied by minus IH bar times ddx. And if it were operating on something, that whole thing would operate to the right. And when you take two derivatives, you know, all the constants can be pulled out in front. So what am I going to get? The minus I get 1 minus I from the first one of these, 1 minus I from the second one of these. And so I think that gives me a minus sign, right? Minus H bar squared over 2m, those are the constants. And then I have two derivatives acting in a row, a ddx times a ddx, which is going to be operating on whatever comes to the right. So that would be a second derivative with respect to x plus whatever that constant alpha is times the variable x squared. And so we could imagine this operate, you know, if I wanted to let it operate on some state psi, which is a function of x and t, a wave function, we would just, you know, let this one act on that. We'd have to take the second derivative of that function, let this one operate on that, and it would just multiply whatever the function was by x squared. Okay, so back to the summary slide here. What this means is that in the final case, if I want to calculate the expectation value of any other dynamical variable, the most important case being the total energy, but maybe kinetic energy or potential energy could be other ones that you've seen before. What I do is just take the corresponding operator. I could write this as Q hat, but Q hat means take whatever function classically it is of P and X and substitute into that same analytical formula the operators for P and X and sandwich it between psi star and psi. So this is kind of amazing without ever knowing what rho is as a function of Q, say as a function of E. We're able to calculate the expectation value of energy just by knowing psi of X and T, or even at a particular time. We could do it just by evaluating that at a particular moment in time. Okay, questions on that logic there? We're going to practice with it in just a second. Now, what about the standard deviation? Okay, so that's a lot about how to calculate expectation values. The standard deviation is easy if you know how to calculate expectation values. And again, this is something that's shown in detail in Griffiths, so I'm not going to show it. But if you want the spread of some dynamical variable Q, the uncertainty or the standard deviation, whatever you want to call it, Griffiths shows that this is equal to the expectation value of that dynamical variable squared minus the expectation of the value of the dynamical variable squared, all under the square root. Do you guys see that in honor? Yeah, so lots of things you know, but it's good to put them all in the same place. So if you can calculate expectation values, here I'm thinking of, this is a dynamical variable. If Q is a dynamical variable, Q squared is another dynamical variable, so we can calculate its expectation value. What I would do is just take the square of that operator and sandwich it between psi star and psi. Okay, so let's try a worksheet as this is one that was posted for Monday, but it's actually being used today because we didn't get to it on Monday. And it has us calculating, here's a nice simple formula for a state psi at a particular time. Just to make sure we're keeping warmed up with normalizing, the first thing I want you to do is normalize that wave function just like we did on Monday. And then we're going to calculate some expectation values and spreads. Okay, so for Alvis and Jake online, look on the course website. It's posted under Monday's date because I thought we might get to it that day, and start working through it. There's actually 2 problems, and I think we're ready to do both problems. We got 20 minutes left, so I may stop us in 5 or 7 minutes and check the first few parts of problem 1, and then we're going to continue on to problem 2. So just keep on working through. If you have a question, certainly shout it out if you're on Zoom, or raise your hand in here, and feel free to work with folks that are adjacent to you as you finish an answer. Get your normalization constant that you should put out in front of psi to make it normalized. When you figure out what A is, check with the person next to you just to make sure you agree. I'm going to put some answers up on the chalkboard here just so you can check as you go. Again, the strange multi-part function is trying to make your work easy in doing integrals. I made this function 0 outside of the range 0 to 2, just so you don't have to worry about divergences. And it's a power law kind of thing, so easy to integrate. Mm-hmm. Yep. Wait, is this a -2 or a -1/2? Oh, I just couldn't see the 1 up there. I see it's yeah, okay, yeah. I just couldn't see the 1. Yeah. X to the 1/2 over 1/2 is 2 times the square root. Yes, so that's, yes. So that's 2x to the 1/2, right? A squared. Yes. So I have x to the 1/2 over 1/2. I think that's what you had, right? Right. So that's this 2 times the square root of 2, right? When I put the 2 in, I get the square root of 2, and then times 2, and 2 times the square root of 2. You know, I can write this as the square root of 2 squared. So that's the square root of 2 cubed. So 2 to the 3/2. So I think you have the exact same equation I have right there, equals 1. Okay, let me see what so you're divided by this, and then you take the square root of that, which changes it to a 2 to the 3/4. When you take the square root of something, you raise 1/2 power. When you raise it to the 1/2 power, that gets multiplied in, let me just, so I can write on something. 2 to the 3/2. We want to take the square root of it. So we're raising to the 1/2 power. And you remember, when you raise things to successive powers, you multiply the powers. So this would be 2 to the 3/2 times 1/2, which is 2 to the 3/4. You know, this is in the denominator, by the way, but just explaining one step of arithmetic. There are different ways to write it too. As long as you're getting the same numerical value, that's fine. But yes. Oh, yeah. Oh, okay. I see. Yes, because you're just, I put it in the denominator. I could have put this in the numerator with the inverted.
Yeah, but I don't think that's still right.
Wait a minute. Wait. So tell me what's going on here. You have 1 over 2 to the 3/2. And that's the same thing as 2 to the -3/2. 1 over 2 to the 3/2 is the same as 2 to the -3/2. I think you flipped over the exponent instead of putting a minus sign in front of it. Right? 1 over 2 to the 3/2 is the same thing as 2 to the -3/2. Is that? I think that's where you made the mistake there. Right. So then my A would be 2 to the -3/4 is another way of writing. Yeah. You agree with me? Okay, that's all right. It's easy for me to get tripped up on these things too. And But you know, you're going to be seeing a lot of this kind of arithmetic and algebra in Griffiths. And so it's important to get back so it's in the front of your mind. Anybody else want to talk about A? Are you guys, you look like you agree with me, right? And you're working together with Tanner there. And you're good on A, Jake? You agree with me? 8 to the, so let's see, if I have 2 to the minus 3/4 is what I have. 2 cubed is 8, so 8 to the minus 1/4. Is that what you said? Yeah, that's the same thing as mine. Alvis and Jake Woosley, any questions on A?
Not I.
No, I'm good.
No, you're good. Okay. Do we need to, so how about B, just to bring us back together for a second? I know several of you are working on C right now. What about B? Without calculating, is the expectation going to be larger or less than 1? Notice our whole wave function is non-zero between 0 and 2. So I'm saying, should we expect it to be to the right of the halfway point between it or to the left? And what do you think? Just to get your intuition. In other words, what does rho of x look like as a function of x? If I were to draw rho of x, well, psi is only non-zero between 0 and 2, right? Here's 1, that's the thing in question, right? So it's 0 outside of there. Psi looks like x to the minus 1/4, so psi star psi is going to look like x to the minus 1/2, or 1 over the square root of x, which blows up near the origin, and then it sort of comes down. I mean, I don't know exactly what shape to draw, but it's going down like that, right? And that means the probability is sort of shifted to this side, which means I'm expecting the expectation value to be somewhere over here to the left of 1, the expectation value of x, because most of the probability looks like it's over on this side rather than over on this side. Sorry, we're looking at 1. Most of it's less than 1 compared to bigger than 1. That's what I'm trying to ask you about in B, just to make you use your intuition. Then you can check your intuition in C. You better get something less than 1. And I got 2/3 there. Anybody want to go through C together? I think some of you have done it and some not. Well, let's just quickly do it. You can ignore me if you want, but doing C here, the expectation value of x is equal to the integral from minus infinity to infinity, just by definition, of psi star x psi dx. Psi star and psi are only non-zero between 0 and 2, so I can reduce the integration range down to 0 to 2. And in that range, psi star times psi is going to be equal to 1 over, let's see, the square root of 8. 1 over the square root of 8. Yeah. 1 over 2 to the 3/2. That's the square of 1 over 2 to the 3/4. You may have written it in a different but equivalent way. Times psi star psi is going to have an x to the minus 1/2 in it. So that's a, x to the minus 1/2 is a 1 over the square root of x. And then I've got to put my x in there. So I've got another factor of x here. And when I combine the x over the square root of x, that's just a square root of x in the numerator. And that's easy to integrate, right? X to the 1/2 is an x to the 3/2 over 3/2. So it looks like that's 1 over 2 to the 3/2 x to the 3/2 over 3/2, which is a 2/3. And then I've got to evaluate that between 0 and 2. At 0, it's 0, but at 2, I get 2, 8, the square root of 8. we could simplify this, and clearly I did simplify it here. It simplifies down to 2/3. So let's see. Oh, I see. I have a 1/2 to the 3/2 times a 2 to the 3/2. Hey, that's kind of nice. This cancels with the upper limit there, and I'm just left with 2/3. Maybe I somehow, when I was doing it the first time, I realized that it was good not to simplify this the way, Jake and some other people did, because, hey, it ended up canceling later. Or maybe that was just serendipity. I don't know. Okay, keep working on D, that standard deviation or uncertainty in X. Usually the way I start it is say, let's calculate the uncertainty squared, or the standard deviation squared. That's just the expectation value of X squared. So I'm sandwiching in X squared between psi star and psi and integrating, minus the expectation value of X, and take the result and square it. And then at the very end, after the dust is settled, we can throw the square root in there. I don't want to have that hanging around the whole time. Well, I'm seeing that it's 12:35. So if I want a chance to go through this together, maybe some of you I think have finished, but others not. We already know the answer for the second part of this, right? We found the expectation value of X is 2/3. So that means the expectation value of X squared is going to be 4/9, right? So that's easy. We've done that work. We haven't done this work. This work is the expectation value of X squared is going to be the integral from minus infinity to infinity of psi star X squared psi. That's my dynamical variable, X squared dx, okay? And again, psi and psi star are only non-zero between 0 and 2. So I can replace that with an integral to 0 and 2. Throw in my numbers. What do I get? 1/2 to the 3/2 power when I square the constant in psi star and psi and put them together. I have an X squared here. And when I put the X dependence in psi and psi star together, I get a square root of X in the denominator, if I remember from before. So this is an X to the -1/2, and this is an X to the 4/2. So it looks like I have to integrate an X to the 3/2, 1/2 to the 3/2 integral from 0 to 2 of X to the 3/2 dx. Just putting in a few extra steps because it's easy to drop stuff in your head, especially when you're writing at the board. Okay. Looks good. That agrees with what I have. So I get an X to the 5/2 over 5/2. So that's 1/2 to the 3/2. X to the 5/2 over 5/2, and 1/5/2 is 2/5. So I get a 2 to the 5/2 power. And at this point, just to sort of, at some point I converted to, no, actually things simplify out quite nicely, and you get 4/5, because this can be written as 2 to the 3/2 times 2 to the 2/2, which is, when I cancel this against this, I'm left with an extra factor of 2 in the numerator. So that's equal to 4/5, right? And therefore, this is 4/5. So I get 4/5 minus 4/9. Find a common denominator if you really want to make it nice. Not my favorite thing to do, but find a common denominator. And then, of course, remember at the end, we wanted sigma x, not sigma x squared. So I got to take a square root of the whole mess. And that's where that root came from. Okay, so the spread is about 0.6. That's saying when you have that distribution that kind of looked like this, and then it went down to 0 everywhere else, you know, that's sort of a characteristic width of it. It's kind of hard to imagine what it is, but 0.6 about. At least if it were 10, we'd know to check our work, right? Can't be bigger than 1 for sure. All right. Questions on that one? Good. I mean, all of the stuff should be seeming familiar, but maybe the algebra or arithmetic is a little bit annoying, but you're going to find that annoying arithmetic keeps appearing over and over again. So it's time to just sort of get used to it. Take a deep breath when you're doing your homework and just do those steps carefully as you can. And if you find that something doesn't make physical sense, right? Sigma x is bigger than the width of the whole non-zero area of the wave function. You're gonna have to go back and check things carefully. Check with your colleagues, right? Check with other students in the class because they're doing the same thing. That is a really good way to find out where you made an error. I will say 2, we can look at 2 at the very beginning of tomorrow. 2 gives us a less kind of unrealistic wave function. Here, this was made to make your calculating life easy, this multi-part function. In 2, we're using a Gaussian, and we're going to have to do some integrals of Gaussians and talk about where to look up some formulae that tell us how to integrate Gaussians next to x squareds and things like that in order to answer 2. All right, anything else? Keep working on those homework problems. Start into 5 through 8. And the next 4 after that are going to be due either Monday or Wednesday. So just keep chipping away at them. Hopefully, I talked to many of you about what was meant by those 3 examples. So you're really going to be digging into those as you go forward with the homework. It's a chance to be creative. So if you have any questions about those, feel free to stay after right now and we can talk about them. Otherwise, see you tomorrow for our 2-hour session in here.
All right. Have a good day.
See you, Alvis.
Let's see. There we go.
Okay. Welcome. Jake, are you hanging out to ask homework questions?
Yeah, I was hoping I could do that.
Okay, good. What one are you looking at?
I mean, I'm kind of have questions about all of them. I was just gonna start with the first one.
Okay. Let me pull out my copy here. Hold on.
Okay.
Yeah, the first one is that really long-winded one, right?
Yeah.
Okay.
And so I felt like I could answer A through E like fine, but I was just like tripping myself up on the wording.
Okay.
Especially for like C, what I said was, which talks about yeah, the exposition, like the average exposition. I was saying for all time, like the average exposition would be to the left of the slope because it's moving slower there. So.
Right. So it's going to spend more time to the left of L over 2 than to the right of L over 2 because it's moving faster every time it's to the right. And so, you know, in a ridiculous limit, you could say, well, what about if it's just sitting at rest to the left of L over 2? Well, then, of course, you're only going to find a case less than L over 2. And it gets closer and closer to that the more extreme it gets, where it's going really slowly on one part, and then it hits the other part and it goes really fast to the end and then slow in the other part. Most of the time it's spending it on the one side. So yes, I agree.
I wasn't sure about the wording of it because it said like considering like a large number of random photographs. So if it was like a random amount of photographs, it's very possible to have like the majority of them actually on the right side because
it is possible, but it becomes extremely unlikely. If it's, you know, let's suppose it spent 99/100ths of its time. Now, this isn't true, but I'm saying in a different case where the upper shelf was really high, so it just barely makes it up there and it rolls really slowly. And then the bottom part is really far down, so it goes really fast up to the top part. Maybe it spends 99/100ths of its time to the left. Now, it's possible if you're taking random photographs that you take 5 photographs and every time it happens to be to the right where it was moving fast. But that's extremely unlikely, and the more photographs you take, the more likely it's going to approximate the probability distribution you know, in terms of what percentage of the time we expect it to be on the left versus on the right. So even though it's possible because they're random, and I'm saying they're random because, you know, when you do measurements in quantum mechanics, we say they're randomly chosen according to the associated probability density function. And so it's the same kind of thing. Yeah, I mean, if I do 5 or 6, it might lean more to one side when really the probability favors the other side. But if you do 1,000, if you do 1,000,000, it's going to very well approximate what the probability density is
Okay.
for those photographs if you bin them up, you know, and make a histogram of them.
Yeah, that makes a lot more sense. And then, but then was tripping myself up with the following parts with like F through K, because I didn't know how to like create the equation for the probability because I did not incorporate like the V's into it if you're even supposed to.
Yeah, so in this case, we are told in just above F in that paragraph that we're going to assume that the system is adjusted so the speed of the ball at the upper level is double, the lower level has double the speed compared to the upper level. And if you think about it, that means it's going to spend twice as much time on the upper level compared to the lower level.
Yeah.
Does that make some sense to you?
Yeah.
Okay. And that means you're going to be twice as likely to find it on the upper level compared to the lower level.
Okay.
So that means the probability, I might write it this way, the probability of finding it on the upper level is double the probability of finding it on the lower level. And of course, it's got to be in this particular problem, either on the upper or the lower level. So the sum of those two probabilities have to add to 1. So I've got to think of two numbers that add to 1. In other words, they're fractions. They're less than 1, and they've got to add to 1. One of them is double the other. The only way that can work, I mean, you could write a system of equations, but that's just saying it's got to be P upper is 2/3 and P lower is 1/3.
Yeah.
Does that make sense? Because they've got to add to 1. It's got to be either on the upper or the lower. And the probability of being on the upper level is double that of being on the lower level. So if the lower is 1/3, the upper's got to be 2/3 because they have to add to 1.
Okay, that makes a lot more sense because I was trying to figure like
that's F and G essentially, right?
Yeah.
And then H is, you know, a little bit tricky, but it'll help you with I and J once you figure out H. So H says, what is the probability of finding the ball's center between X and X plus delta X on the upper level? So here's one way to think about it. Let's draw a little cartoon here. Here's my potential function. Here's L over 2 there, right? And so here's the x-axis going through here. Let's say here we are on the upper level. Here's X, and here's X plus delta X, right? We want to find the probability of being in that range that I've shaded in there. Well, we know the probability of being anywhere in this range is 2/3, right?
Yeah.
So, and the probability is the same all the way across here. So the probability of finding it in the smaller region is just the appropriate fraction of 2/3. Let's see if we can do that, right? I mean, I'm going to say, if the probability of being here is 2/3, this is something less than 2/3. What's the appropriate fraction? So I might write this as the probability of being in the range X and X plus delta X would be some fraction of 2/3. And the fraction, the appropriate fraction is going to be this length out of the total length.
Yeah.
Right? So this length is of width delta X. And the total length is of width L over 2, right?
Mm-hmm.
So if I simplify that would be 4 over 3L times delta X. if you just put some stuff together there. Okay, so that's not so thrilling, but now I can use that. So any questions on that one before we go on and talk about I?
No, that makes sense.
Okay, now the probability density, remember what the probability density is. We said one way to think of its definition is rho of x times dx is equal to the probability, maybe I could write it this way, the probability of being in the range x and x plus dx. So I'm going to calculate, so another way of writing that is rho of x times delta x, as long as delta x is small, is the probability of being between x and x plus delta x. And we want our delta x to get really small to approximate a dx. So I've already got what the probability of being between x and x plus delta x is. What it's telling me is to find rho of x, all I have to do is divide that thing I got over there by delta x. So that means in this case, rho of x on the upper level only is going to be equal to 4 over 3L. That's for x less than L over 2. Okay, so we're trying to figure out if we wanted to graph what rho of x is. I'm not sure if I asked you to do that. Yeah, in K, you're drawing a graph, right? Here's L over 2, here's L. That's as a function of x. We've just found out, right? We said when I find the area under the curve, the height rho of x times the width delta x, that's the area under the curve. That's the probability of being in that range. And therefore, if I want rho of x, all I have to do is take this probability and divide by delta x. And we just found that probability. So all I got to do is divide by delta x. That makes it disappear. 4 over 3L. So if I'm drawing rho of x, it would be up at height 4 over 3L on the upper level. It's 0 over here, of course. It goes up to 4 over 3L there. And you could repeat the argument, but it's pretty clear now that on the lower level, it's going to have half the probability density, right?
Yeah.
So this would be going down to 2 over 3L over there, and then jumping down to 0 forevermore. And you could even, just to check your work, add up the area under this curve. It better add up to 1 because the total probability's got to be 1, right? So I have L, if I find the area under the curve, that would be 4 over 3L times L over 2 plus 2 over 3L times L over 2. And I cancel my L's. That would be 1/3 plus 2/3, which adds to 1. So the total area under the curve is 1. That looks like everything's working out there.
Awesome. Yeah, that makes a lot more sense. I was like overcomplicating the first part of it, like in terms of looking for the probability. Like I was trying to follow like the reading, like it was giving us equations for probability. And like I don't understand how to incorporate speed.
Yeah, I mean, so here, there's nothing really in the book that would tell you directly how to do this, but rather than applying a formula, it's more like we just need to think about this problem, in the right way, and then it just pops out easily.
And then let's see.
Makai, do you need to go somewhere, or did that answer your question? Okay, good. Okay, Jake, go ahead.
Well, I realized I could fix this. For 3, I was trying to read it off like the website at first, and I couldn't read like all the subscripts and superscripts in part 3, but then I like actually downloaded it and it was able to like zoom in.
Yeah, I've had that problem too, whereas if you view it in the browser, it screws it up, but if you open it in Acrobat, everything looks fine. So I would just suggest downloading and opening in Acrobat.
Yeah.
That seems to fix everything.
Okay. So I haven't worked through that yet because I was gonna see, like, I just solved that like issue myself. I still work through part 3, but then for question 4, where we're supposed to like give different examples of non-normalizable full wave functions. Like, I wasn't sure, so I tried like Googling, like just to get like on the right path.
Yeah.
And so like it said one would be a plane wave function. Is that?
Well, so the idea is you're going to give a psi, and then so when we take the magnitude squared, it's if we integrate the magnitude squared from minus infinity to infinity, and we find any finite number, it's going to be normalized. So there are two ways things could go wrong. Either the integral of psi star psi from minus infinity to infinity is 0.
Yeah.
And then there's no way to put a constant in front of it to make it big enough so that the area under it is 1. If it's 0, then any multiple of it's going to be 0. The only way that will happen, so this is kind of a unique one that some people may use, is psi of x at time t0 is just, the function 0. That means it's 0 everywhere on the x-axis. When I take psi star psi, that's 0. When I integrate from minus infinity to infinity, it's 0, right?
Mm-hmm.
And we said, oh, if you want to normalize it, you multiply by 1 over the square root of whatever that integral is. Well, the integral is 0. So when I take 1 over the square root of it, I would have to multiply by an infinite constant. So this is non-normalizable, this function. That means 0 everywhere. But the other way that's the only case that will actually be non-normalizable because the integral is 0. The other cases that don't work, and almost any function you name, like if I say, give me a function of x at time t0, what's the function of x going to look like? Name a function.
You asking me name a function?
I'm asking you, yeah, just name a formula for a function that you would have seen in a math class anywhere. Doesn't have to be complicated, could be super simple.
Just like sine omega t.
Sorry, you said sine what?
Omega t or sine theta.
Yeah, so let's just say, because we're talking about functions of x, right? We evaluated a particular time, we want a function of x. Let's say sine of x.
Okay.
You just made that up. That's psi as a function of x at a particular time t0 is sine of x. So that means psi star psi is going to be sine squared of x. Okay, you know what the graph of sine squared of x look like? Well, sine looks like this, right? It goes up towards the maximum and then down like this. That's a graph of sine. When I square it, of course, the negative parts become positive. So the graph of sine squared of x is going to look like this. It's got a bump there. That's between pi and 2 pi. Here's between 0 and minus pi. Of course, there's an infinite area under this curve. When I integrate psi star psi from minus infinity to infinity, these are going to keep adding up bigger and bigger because I've got an infinite number of bumps there. So that's what we call a divergent integral. As you integrate farther and farther out towards plus infinity and minus infinity, you get something that keeps getting bigger and bigger. That's one way to be divergent. So that's a good example. Sine squared of x. What's another function? X squared. What's another function? X. What's another function? 1 over x. You can try all those. They'll all give divergent integrals.
Okay.
Right? So for example, if I say my psi is at time t equals 0 is just x. That means psi star psi is x squared. And if I integrate from minus infinity to infinity x squared dx, are you willing to believe that that's a divergent integral? In other words, it's going to infinity because the area under the curve, here's x squared, right? It's a parabola. The area under the curve, whoa, there's a lot of area there, right?
Yeah.
If you do x cubed over 3 and try to evaluate between the two limits, you'll get infinite values at the limits. So almost any function you can come up with, it's really hard to make a function normalizable. Turns out the Gaussian function, e to the minus x squared, is normalizable. Doesn't have an area 1 under it, but it can be made to have an area 1 under it by multiplying by something. So the hard thing is to make normalizable functions. So make non-normalizable functions, you just, don't make them too similar, but here were just 3 easy examples. Name another one. E to the x. right? If psi is e to the x, then psi star psi would be e to the 2x. When you square e to the x, you get e to the 2x.
Mhm.
And you find the area under that curve, right? If I graph e to the 2x, it's still going to kind of look like e to the x. Looks like this, right? What's the area under the curve? When I integrate from minus infinity to infinity, I get an infinite area. And it's only when this integral from minus infinity to infinity of psi star psi dx, if it equals some non-zero, non-infinite number a, in that case, we can normalize it. But in almost all cases, when you just grab a random function of x and put it in there, in most cases, it's just going to go to infinity, unless you're really, really careful.
Okay. Yeah, that makes sense.
So the more challenging problem you'll find is problem 5. And we can talk about that tomorrow if you want. In problem 5, I'm asking you to give 3 different examples of normalizable wave functions. And I want them to be quite different. So there you're going to have to be a lot more creative. But in this case, you can just randomly shout out 3 functions. And I guarantee none of them are going to work unless you chose one of them to be a Gaussian function.
Okay. Awesome. Yeah, that was the majority. That was the questions I had for 1 through 4.
Yeah, sounds good. So keep chipping away at these and we can talk about them tomorrow. Again, I'm going to have you turning 1 through 8 on Friday.
Okay.
So if you have problems on 2 and 3, just ask me about them tomorrow and we can go onward after class tomorrow.
All right. I will do that.
Sounds good. Glad you could stay after today.
All right. Thank you so much for that.
Hey, no problem. See you tomorrow. Bye.
Yep.